Today I'm gonna discuss harmonics in power system that affects the power quality. So harmony actually is defined as a electrical pollution. So what is the harmonic actually? So anything that deviates from the normal sinusoid. So in all the electrical appliances is powered by a sinusoidal voltage source, so it's a 60 hertz voltage source. So when it deviates from the normal sinusoid, then it's become a pollution and the waveform will be distorted. So here we show there is a two type of lamps. So it's a spiral one, and this is just for incandescent lamp. So this is the linear load and this is the non-linear load. So there is a great impact of load nature on harmonics in power system. So the harmonics just we're talking about here. This is the graphical illustration is here. So this is the time, this could be the amplitude of voltage or current. So the red one is the fundamental, this is a 60 gigahertz, whereas the white one is the third harmonic. So here there is a 3 cycle in the first half cycle of the fundamental wave. So it is recognized as a third harmonic, whereas the fifth harmonic there is a 5 cycle in the first half cycle, so it can be recognized as a fifth harmonic. So if we add all the waves, then we will get this yellow one. This is the resultant, so it's just a distorted wave. So we are supplying the red one, but we're getting in the load end is the yellow one, so it's not our objective. So let's start with definition. So in the electric power system, the harmonic could be in the form of voltage and current, as I earlier said, and its harmonic is produced due to the action of nonlinear load. So different type of nonlinear load is it can be rectifiers or the dimmer switches and the photocopiers, the printers, TVs. So actually all the household electronic equipment are the non-linear loads, and the linear loads could be the iron or the incandescent lamp, where there is just only a tungsten, is a resistance is inside the bulb. So yeah, the linear load doesn't make any impact on the power quality. So here is the example. So the you see the blue one is the voltage curve, whereas the red one is the current curve. So it's both sinusoidal. There is no problem with that. The system is just supplying the sinusoidal voltage, whereas we get the sinusoidal current wave. But in this figure, so it's for incandescent lamp, here we show. So that there is just only a resistance. So I equals V by Z, so Z equal to R. So here's the voltage and this is the current. This is lowered because there is an impedance effect that reduces the amplitude of current. But here in the right hand side is the diagram for the spiral 42-watt lamps. So here is the same source supply the sinusoidal voltage, where it's getting the distorted from of the current wave. There is a spike here, there is a spike here. So yeah, this is definitely reduces the power quality. And now later on we'll show how harmonics affect on power quality. So harmonic is just nothing but a frequency. It can be expressed in frequency domain. So it's an integer multiple of the fundamental frequency, and the fundamental frequency could be either in 50 hertz or 60 hertz. So in North America, 60 hertz is the standard, and the second harmonic could be the second harmonic is 120 hertz, and third harmonic is the 180 hertz. So likewise the higher order harmonics. So when the multiple waves are combined, they just form a complex wave. So the in complex wave, this is just a distorted signal. So if we just give an example as a E1 for amplitude wave, this is the pure this is the time domain in here, and this vertical axis is the amplitude. It could be the voltage or the current. So amplitude of sine wave at wave 1, so this could be the wave 1 at time t1. So here's the time, for example, or here at any instantaneous time. And E2 is the voltage. Here actually you just consider this. E2 is the voltage of sine wave 2. So if you just sum of this, then we'll get a complex wave. Now see how it's happened. So here is the fundamental wave, and you see is the third harmonic wave, because in the first half cycle of the fundamental wave, just go down. Yeah, sorry, it's a 1 3 1 2 or 3 half cycle, so it's a third harmonic actually. So in the first period there is a sixth half cycle, so it's a third harmonic. So if we just add to these two, then we'll get this one. So this is the actually this is the resultant ET, this is the ET, and here's the E1 at any point. It could be here, this is the point 1 T1, this is the T1, and here is it could be the T2. So if we just add this, then we'll get the complex wave. So it's nothing but a complex wave. So harmonic if is integrated, it's here. So so here you can see that this is the clean wave, this is the just sinusoidal, and while this is the dirty power, this is generated due to the harmonics. And here's some example of second harmonics. So the gray one is the fundamental one. So in every figure the gray one is the fundamental one. So it's the second harmonics because there is a two half cycle under the first half cycle of fundamental wave. So it's just 150 wave because the period is reduced, and then the frequency is higher. So it's just it's a second order harmonics. And likewise, this is the fourth harmonics, this is the fifth harmonics. It's all depends on the time period or the frequency. I mean the number of cycle in a period. Okay, so here if we just divide the harmonic wave, we'll get the above figure, this figure. So if we demodulate this one, then we'll get this, and if we sum this one, then we'll get this. So it's actually is a bidirectional process. So here it is shown in this figure. So this is the harmonically distorted waveform. So if we distract it, then we'll get this is the third harmonic component, and this is the fundamental component. And this figure this figure is the same because here is just this is a fundamental one, and if we just add or plus this third harmonic, so it's a sinus, this is a sine wave and this is a cosine wave, both are sinusoidal. So we'll get this wave shape. So the shape of the wave is can be derived by the Fourier transform. Later on we'll see how could we derive the wave shape here. So it's just this both curve is a harmonically distorted waveform. So whenever these two waves combined, then we'll get a complex periodic wave, as we mentioned earlier. So now see how the complex periodic wave we can obtain here. So it's a 3 hertz signal. You can see this is the first period. So t so it's the t is 0.33 second, then the frequency will be 1 by t, so it's a 3 hertz. So here the first period is 1/5 times, so the frequency is just a 5 hertz. And if we add these two, and then we get this one. So here we see this is the first half cycle and this is the second half cycle. Just repeat the second one. So it's just a complex periodic wave. This is the harmonically distorted waveform. So here the period is 1, so the frequency is 1 hertz. So the combination of 3 and 5 will get this one. So now the Fourier transform. So Fourier theorem. So actually we know the Fourier series is used for the conversion of from time domain to frequency domain, whereas the Fourier transform can transform the any linear or non-linear waveform into frequency domain, whereas Fourier series is used only for determination of linear curves. So Fourier transform can be used for harmonic analysis. The same principle is here. The sinusoidal components, if we divide the sinusoidal components of complex periodic wave, then we will get the fundamental component as well as the harmonic component, and the harmonic component is the integer multiple of the fundamental frequency. uh, so this is the expression of Fourier transform. So this is the DC part, and the cos part is known as the even part, whereas the sine part is known as the odd part. So there is a specific reason to designate it this odd and even signal is here, because the sine wave we know in the power factor. When we read the power factor, so the reactive power, this is the useless power, wasted power, is related to the sine component, so bi sine theta, whereas the real power is related to the cos theta. So in power system we are greatly concerned about the odd part. Later on we'll see why we are concerned about this. So this is the fundamental angular frequency. So if we put the value over here, then we'll get this equation. Then if we extend this expression, we can get this is the multiply in the both side, and then we'll get the cos A cos B 2 cos A cos B plus 2 sin A sin B, because here it's just a this is the amplitude of real part. Here go up. Here this is the amplitude of the real part, I mean the horizontal component cos theta. So here is the real, and here is the for vertical component with related to those signs. So if we just divide the expression, I mean the rectangular, so here is the exponential from, for example, z equals x plus jy. So in polar form it can be expressed as z equals j theta, so z equals x squared y square, and theta equal to tan inverse 1 y by x. Or in trigonometric form it can be written as in exponential form is e to the power j theta, but in trigonometric form it can be written as cos theta j sin theta into z. So the real part is actually related with the cos theta, and the imaginary component, this is the vertical component, is related to sine part. So here we see an with the cos omega n, so an is the horizontal component, whereas the bn sine theta is the imaginary term, so it's related to here. So according to Pythagoras, this can be written as a square an square bn square. So here's the theta. So cos theta can be written as this, and sin theta can be written as this. So here we'll get this equation. So it's a generic form of the Fourier transform. And so now I will discuss the key element of poor power quality. So there's a three factor actually here. There's the harmonics. So harmonics can happen due to the nonlinear load and the reactive power. So it's could be for the inductive load, because the inductive load current is lagging. So due to the lagging nature, so the real power will be reduced from the apparent power. And there is another reason, this is the load imbalance. So if there is a imbalance between three phase load, so it could be reduce the power quality. So here is the example. This is the just a previous example is here. So this is the fundamental one, this is the third harmonic. If we just uh, add here, then we'll get the distorted waveform. Here is the power spectrum. This is the voltage or current shape, and this is the power spectrum. So this is just a fundamental frequencies here, and this is the lower amplitude in the third. This is the fundamental element of, this is the for first position, and this is in the third position. And if we just add, just like a spike, because we know the Fourier transform, if we just cos theta, then we can get pi delta omega, or just theta actually is omega t. So omega or omega naught t is delta omega plus omega naught t. So if we just draw the spectrum, we can get, this is omega naught, and this is minus omega naught, and the amplitude is pi. So we're just considering the single side band. So if we just consider the single side, then so there is a spike here only of the fundamental, and this is the here is in the third position, because this is the for fundamental, and what would be for, this is for cos 3 omega t, and then we'll get spike. This is the 1 minus 1 and minus 3, sorry, so plus 3, minus 3. The amplitude is lower because you see here is the amplitude is lower for the third harmonic as the order of the harmonic is increases, and the power of the signal, this is amplitude of the signal, is reduces, because power is directly related to the amplitude of the voltage or current, because P equal to A square by 2 for the sinusoidal signal. So as the amplitude A is the amplitude of the voltage or current, so if A is reduced, then power will definitely reduce. So why we need to analyze the harmonics? Because so actually there is a two type of harmonics. One is a voltage harmonics, and another is current harmonics. So harmonics can causes heating and sometimes weaken the insulation and malfunction of electronic devices, and it could cause a electromagnetic interference. So there is some and heating loss. So there is some several effects because of harmonics. So now we just make a difference between current harmonic and the voltage harmonic. So in normally, so in power system, when the load is linear, so the sinusoidal signal of 60 hertz voltage is applied. So when the linear electric load is connected to the system, it just draw a sinusoidal current the same frequency. But current harmonics are caused due to the nonlinear loads, as I said in earlier, and the nonlinear loads could be the energy saving spiral lamps, UPS, fax, photocopier machine, printer, and our laptops. And so yeah, these are the example of the nonlinear load that creates the current harmonics. And so these nonlinear loads create the distortion of the pure sinusoidal wave and may result in the resonance, I mean the vibration of the electrical vibration. So in power system, we are not concerned about the even harmonics, because due to the symmetry, because in the full in a positive in a period there is a half positive cycle and then there is a negative cycle. So this due to the symmetry of nature. So here is the positive half cycle, the average value is 0. So due to the symmetry over a cycle, this we are not concerned about the even harmonics. So only in power system is concerned about the third harmonics, because you know in the power system the entire spherical is 360. So in three phase, each phase can be 120 degrees apart. So yeah, there is a reason behind this, because the generating station are designed for the three-phase system, three-phase generator that is connected to three-phase via a three-phase power transformer. So yeah, so for the three-phase system, three-phase load, so the source I mean the generator is connected to a three-phase transformer, and then output secondary side of the transformer is connected to the three-phase transmission line, and then transmission line is connected to the three-phase load. So yeah, so here we are just concerned about the three-phase, and so you see here's the phase one. So it's just a phase difference 0, and for the second phase it's just a 120-degree apart, and the third is 240. So if we just write the equation here, for example, if it is a voltage B equal to Bm sine omega t, so for second one sine omega t minus 120, and the third one is the peak voltage, maximum voltage, sine omega t minus 120. So it's for B1, is B2, and is B3. And here, so is the third harmonic is existing is here. So third harmonic is always the key constant of the power systems. So to reduce the effect of third harmonics, so delta connection could be used in the either in the transformer or in the transformer or motor or the generator connection. So it can be used as an attenuator. So in delta connection, the harmonic effects can be reduced, and the voltage harmonic is just similar like a current harmonics. It caused by the actually the current harmonics. So now we see the example. Here there is a voltage of the sinusoidal wave. This is the peak voltage, this is the maximum voltage is here, and the nonlinear load impedance, the load value is not given in this example. So the current is here. There is a three part. This is the fundamental part, because here there is only one, and this is the second harmonic, and this is the third harmonic component, and there is no another harmonic considered in this example. So we have to calculate the real power, reactive power, and the displacement term, and also the displacement factor, distortion factor, and the power factor as well. So now let's go to the solution. So it's the voltage B, and the current is here. So the RMS value, we know the RMS value, it could be the voltage or current written as this is the peak voltage or the maximum one divided square root 2. So so is 200 root 2 is the peak voltage, where is the this is the RMS voltage here, this is the RMS one, and this is the current square. So you see the amplitude here, this is the RMS current for the fundamental component. For the second harmonic, RMS current is 10, and 10 for the third component. So if we square, then we'll get this one, and the apparent volt ampere just can be this is A equal to VI, as we see, because the apparent power is equals VI, real power VI cos theta, and the reactive power is VI sin theta. So we just square root, and then we'll get only the volt ampere value. So here real power is VI1 cos theta. So why there is I1? This is I1, this is I1, this is I1, this is I2, and this is I3. This is the first, second, and third harmonic component. This is the fundamental. So why this is I? Because the real power is only transferred through the fundamental component. So here this is only I1. So no I2 or I3 or I4, whatever the value. So no values be considered here. So now the B RMS value, this means the RMS value 200, and the I1 is 20 is here, and the cos theta, cos psi 1, here is the cos value is 45 degrees here. So you'll get this value, and the Q equal to B I sin theta. So for we know cos 45 and sin 45 is 1 by root over 2. So here we'll get the power, and we know, so So S can be written as P square or Q square. So according to power triangle, S is the apparent power, P, so sorry, here is the Q and is the P is the power factor angle theta. So yeah, so so if we just S square equal to P square plus Q square, if we just add these two terms, we will not get this one. So there is a difference, there is a displacement is here due to the harmonic component. So we can derive the d square equals this is s square minus p square minus q square, and we'll get this value. So this is a p, this is q and sorry, and this is d square, and if we just root 2 we'll get d. Okay, so here now we have to find displacement factor, distortion factor, and the power factor. Let's go to the next part. Yeah, the power factor is defined as yeah, here you see the power factor cos theta equals p by s. Here power factor is p by s. P is the real power, s is the apparent power, so p equal to pi cos theta. Yeah, and this is the apparent power, this is actually the total current, and the real power is flow through the fundamental part. This is why we used I1 here. So now the displacement factor is cos psi 1. So we see cos psi 1 is 45, this is 1 by root over 2, and the distortion factor can be defined as I1, I2. I1 is 20, here I1 is 20, I and I is this is the I, yeah, this is the I, because you see it's 600 ampere square. So if we root, then we'll get this root over 600, and then we'll get this one, and the power factor would be, just put the value, I1 divided I is 0.812 by root 6 or 0.8167, and cos psi equal 0.707. If we just multiply this, we'll get this. So this is our answer. So now see the wave profile in commercial building. So here you see there is a generation source is here, and then this is the watt meter, measure the power of the system. So this is the power transformer. So here as the source there is an ideal transformer, it's a 14 kilovolt. You know, the generating in voltage is normally 11 to 15 kilovolt. So here is a pure sinusoidal wave. So as long as it crosses, here is a transformer, it's a nonlinear one. So 2.8% total harmonic distortion. So yeah, so here is a harmonic factor is included here, and the shape is gradually changes, as well as the voltage is getting reduced, because this is the step down, and you know, as the harmonic power is increases for the second harmonic, third harmonic. So as we go in the upper order, and the amplitude is goes down, and you see there is a three nonlinear for three-phase system. This is a three nonlinear loads. So here the total harmonic distortion THD is getting increased, and the shape of the signal as well as the voltage is getting reduced. And here and eventually at the receiving end we are using our laptop here. So here the shape, this is a complex periodic wave, this is the harmonically distorted waveform. So here the harmonic percentage is increased, so the shape as well as the voltage amplitude is getting reduced. So this is the typical scenario in our house. So what is the technique of remedy? So there's a multiple solution is there. So most lucrative solution is the using active or passive harmonic filter. So the principle is here. So just commercially they just develop this device in such a way that so here's the fundamental wave. So if we just this is the fundamental wave, this is just one spike. So and then the load current, so the load current, so here is our load Here is our load, here is our another low voltage load, this is the high voltage load. Because the load rating is higher, so it's directly connected to this transformer, and then we are using the low rating voltage. So here once again we used transformer here. So whatever the load, the we will get the distorted current like this one. There is a harmonic component is associated here. This is the second, this is the third, fifth, seventh, likewise. So what is the remedy technique? So if we add the active harmonic filter, just cancel out this component. You see this component, this is the negative side, this component cut this one, this cut this one, this cut this one, and then only remains this one. So this is the fundamental one that we're looking to extract. So this is our desired one. So here's the principle of cancellation of harmonic by equal and opposite harmonic generation by an active filter device. So here there is some standard is defined by European standard IEC, and there is another standard that the load, the different kind of load can be categories in class A, B, C, and D. And there is another standard, the most popular standard is IEEE 519. So now there is a 2014 standard is there. So yeah, and so here the IEEE standard limits the harmonic at the entrance side. This is at the source inside, and whereas the European standard is applied at the load end side. So here I just show I just present the for load inside. So it is the European standard, and similarly the IEEE standard is a North American standard. Is can be typically applied in the source inside. This is the generation inside. So yeah, there is a pre-compensation, it's like a pre-compensation, and there is a post-compensation. So both can be integrated in a system to compensate the harmonics. So that's it for today. Thank you everyone. Have a good day.